let's give it a start. My name is Chiara. I work for European Bioplastics. We're here today for our talk number 5 of this series that we started in 2026, looking at material solutions, bioplastics beyond packaging. And today the talk is about agricultural applications. We're having 2 speakers with us. And before I leave the floor to them, I would like to just walk you through a few things and few reminders. European Bioplastics is the association that is working for advocating for a better legal framework for bioplastics in Europe. We have been up and running for 30 years now, and we collect more than 75 members across Europe and also beyond Europe. So this is, an association that is open also for you to join. If you're interested, come and join forces with us. We're very happy to understand what needs you have and how to represent you at European level. Few things. I would like you to take out your mobile phone. So if you can point at this QR code, this is the invitation to register for the conference that we're organizing in December in Berlin. This is our annual conference, 1st and 2nd December, organized by my fantastic colleague Denise. And please, you can scan this QR code now. You will receive the slides in any case later. And there is a second QR code that you can scan that is related to the call for papers. So if you would like to contribute to this conference, we are accepting papers until the end of June. There are different topics that you can cover with your knowledge and expertise. Just have a look at this page and submit your abstract if you would like to join us and have the opportunity to present at the conference. A disclaimer, this format is mostly funded by the European Union through different projects. Also, some of the speakers today, they will mention some of the projects where they are involved. Some of them are also funded by the European Union. This means that the views and the opinions that you will hear today, they are those of the authors, but they do not reflect those of the European Union, nor the ECB, nor European Bioplastics. Just a little bit of information in advance. Structure of the talk, if you have been here before, you know that we have normally 2 speakers. So today we got Patrizia Marie Schmidt and Sara Guerini with us, and I will be your moderator also for the Q&A. The 2 presentations of the speaker will be around 15 minutes each, more or less, and then we will go into a Q&A with all of you. I'm still buying time for people to come in. If you want to sign up for the next appointments, we have settled down the date for the last appointment of this series. This is going to be on the 7th of July. That's a Tuesday. We will be talking about bioplastic applications in medicine devices and hygiene products. So we're very happy that the 2 speakers are confirmed. The registration is open. You can find it on our website, and we will send you a reminder after this intervention. Housekeeping rules. So you have noticed that all your microphones are on mute. At the moment, this has been set per default. The chat is still active, so it means that during the talks, you can use the chat anytime for typing your questions. By the time you've got questions coming up in your mind, use the chat, and the speakers will have a look at them only after the 2 presentations are over. So we have a joint Q&A. And during the Q&A, you have the possibility still to ask questions in the chat, or if you want to speak up, then you can also raise your hand. We might decide to give you the voice and to give you the possibility to unmute yourself. A reminder, the presentations and the recording will be shared. They are normally put in open access. We delete from the entire recording the Q&A. This is a private moment for us just to share. And next time is also, let's say, this is the way we run this format, so it's possible for everybody to be comfortable in expressing opinions. So today I'm here with Sara Guerini. She's working for Novamont. Sara will be giving us several examples of use of bioplastics in agriculture. Patrizia will integrate this with the products that are coming from BASF and with a talk specific on the fragmentation and mineralisation of soil biodegradable mulch films. A few reminders again, the 7th of July, the next talk, as we said, the medical devices and hygiene products. This is also up on our website. And then, if I may, there is one other reminder. We have an interesting talk, which is partly related to the agricultural sector, but I thought it would be interesting maybe also for this crowd to know that we will be talking with VTT about the project Superbark that is also using industrial softwood bark for high-performance adhesives and coatings. So if you're interested in this topic, you can also sign up on the 23rd of June, and I will put the link to the registration in the chat. Okay, now it's time for me to stop sharing my screen. And I will pass the floor to Sarah, and I will put you in the spotlight so everybody can see you. Excellent, Sarah. Would you like to put your presentation on top of the screen?
Yes.
Yeah.
Well, in the meantime, good morning, everybody. There's a huge amount of people joining, so super good.
Yes. Excellent.
Okay, I hope you can see my presentation.
Yes, Sarah, thank you for this. Please, you got the floor.
So,
thank you.
Thank you. Thank you for the invitation and the possibility. So today I will talk about the use of biodegradable and compostable application for agriculture, excluding mulch film. Because on mulch film, probably many of you are very aware of what is a mulch film, biodegradable mulch film. Can be used. Mulching is probably the most developed application commercially as well for biodegradable materials. So I will skip that because many other applications in agriculture can be really useful to give a sustainable solution for the end of life of plastics. So I will start with this slide, which gives a bit the idea of what is plasticulture. So the use of plastics in agriculture. Here you find some numbers on what the plastic materials mean for agriculture. They're about 3 to 5% of the global production of plastics, and they're growing. They're growing in their use, meaning that the use of plastics is linked to better production, to optimization of use of pesticides and water, and many devices and many applications of plastics are used in agriculture. So it's for sure something positive, but the end of life cannot be so positive. So what am I going to focus is strings, clips, nets, pots, all these types of plastic, which are greatly used by growers, but might be difficult to retrieve from the environment and properly dispose. And all of these group of tools represents about 25% of the agricultural plastic waste. And in Europe, all plastic waste reach 5% of plastic waste. So it's not big numbers, but you're probably aware that microplastics is one of the big topics in different areas. And in agriculture, microplastics can be also reduced using the correct materials or the correct way of dispose materials. So
Sarah, you're on mute. Please unmute yourself. Something happened with your microphone.
Okay, can you hear me now? Okay.
Yes.
So when we're talking about the use of biodegradable or compostable materials, we're talking about a possibility to mitigate environmental risk connected to the persistence of plastics in the environment. So the residence time of plastic material in the environment influences its exposure. So the longer persistence lead to accumulation and higher exposure to the environment. Therefore, when we use a biodegradable or compostable material that has a shortened residence time, orders of magnitude lower, we can for sure reduce the risk connected for dispersal of permanent plastic in the environment. Let me go. Sorry, I got some. Okay. But again, which are the application can be target for biodegradable and compostable plastics? As I said before, mulch film for sure is a clear example of an application which can be happily and fully substituted for vegetable crops with a biodegradable in-soil material. But in order to reduce the risk in the environment, for sure, it's important when we want to talk about where biodegradable and compostable plastics are used. To reduce the risk, we should see the extent of the use, so how much are used. Do this material have a short lifespan? Because this means a high turnover, and if we use conventional plastic, high turnover means we keep loading or potentially loading the environment with more plastic that needs to be well recovered and retrieved. So short lifespan, generally items with a short lifespan can be a target for biodegradable and compostable plastics. Then if they're difficult or expensive to remove, and again, the example of the string and the nets are a good example. And maybe if there are no possibility for recycling facility in the area where they're used. I will show you an example. Obviously, high possibility of leakage in the environment. So any type of plastics which cannot be properly removed or left in the environment because it's impossible to remove, it's a hot spot for production of microplastic. Again, for example, mulch film has many of these characteristics, plus it's highly dirty or contaminated with soil or other materials. These, according to our experience, are the, let's say, main reasons why a biodegradable or compostable material can be useful to substitute a conventional plastic. So our approach in developing application for agriculture and forestation follow what I've just said. So we can use a biodegradable, or in this case, the first example, the first column on your left, an industrial compostable material or tool can facilitate the collection and the end-of-life management. Again, clips, strings, nets will, as I will show in a minute, will for sure make the life of a grower much easier in terms of how to deal with a mixed and what it is now a mixed waste, which can be converted in a uniform compostable green waste that can be then taken to a compost place and be composted. Again, those applications like tree shelters, infill, which have a high risk of dispersion in the environment or are impossible to remove, infill, for example. In this case, biodegradability in soil is the feature we're looking for, and these materials, this application can be happily used in a field substituting conventional plastic. Again, other examples are use in soil and impossibility of removal. In this case, I just explained the example of turf reinforcement nets, which at the end of the life, if not biodegradable in soil, would basically remain entangled with the roots of the grass in the soil. So just a few examples of biodegradable and compostable application we can use, and in many cases that are already commercially available. Another example, I don't know if you see my arrow, are the controlled release fertilizer. I didn't put this in the presentation today, but they for sure represent a good way of using our biodegradable in-soil materials. Up to now, these products, which are present on the fertilizing product regulation of the EU, are not, well, since 2024, a delegated act from the Commission said that the cover for this fertilizer must be in a biodegradable material. The Commission also in this delegated act gave the rules, what is biodegradability for these materials. This is extremely important because it is sure that when we were using a non-biodegradable plastic cover or coating, plastics were remaining in soil. And in this case, since 2028, biodegradable in soil covers will enter into force. And this is a step forward, for sure, recognized by the Commission. Here we go to some examples. This is an example I'm taking from a broad field experiment we carried out a couple of years ago in Almeria, together with Biocrop Science Spain. Biocrop Science Spain had the need to substitute the plastic material used in the greenhouse to increase the sustainability of their cultivation. And we provided clips and strings made out of compostable materials. And we tried them on different crops. We tried them on, basically tomatoes, but also aubergine, peppers. And what we assessed first was how these materials can be compatible with a long time of use in the greenhouses, and also with the situation of greenhouses in terms of temperature and humidity, which really strong, and they can affect the performance of these applications. We use them on over an area of about 80 hectares of greenhouses. So it is an experiment, but it's a broad experiment. And at the end of the crop cycle, where we could assess the complete equivalence of these materials to the traditional ones in used by Bayer, we took all the green waste together, obviously with the entangled clips and strings, and we took them to a nearby green composting plant, which is SAC. Here I show you the experimental composting test at SAC, where a composting pile an experimental composting pile was made using all the green waste from the greenhouses and was left to compost in a normal composting cycle there. The results, it's a compost. Here you can see on the last picture on the right is still a bit rough, but it needs to be refined before used. But we could demonstrate also here in a real composting condition, that the biodegradable, the compostable string and clips were absolutely in line with the requirements in terms of time and process to produce a compost that in this case didn't have any plastic material in. The good point of this is that SAC, after the trial, decided to put a different fee for the material entering into its plant, meaning that they recognize that compostable material can be a real solution and close the carbon cycle, producing a compost, first of all, producing a compost. Before, they had huge problems in producing something which was a real compost with no plastics in. Now they could really produce a compost with no plastics, and this compost can be used to bring back organic matter to the nearby soils. So this was a real good example on how technology and application of compostable material can solve a real problem, because SAC had heaps of piles of compost with a lot of strings and clips and tangles. And as you can imagine, the cost of removing, the labor cost of removing these materials is extremely high. Another example, following our idea of how compostable and biodegradable material can help in agriculture, are the soil biodegradable tree shelter. Tree shelters are used not only for forestation, but they're also used for orchard trees, for vines, to protect in the first years of the growth, the young trees. And in many cases, especially for forestation, it is very difficult that they will be removed from where they used. So Novamont produced biodegradable in soil materials that can be used to produce mesh type tree shelter. They've been used in real field condition for 2 years, and now they're commercially available. Again, we limit the possible dispersion of non-biodegradable plastics in soil. Finally, we go a bit further in Europe on this project. The project finished a few years ago, but again, I normally like to show this project because it's a clear example on how we could solve a problem where in an isolated, it's an island area, where no facilities for recycling plastics are present. Martinica has an enormous area cultivated in bananas, and bananas are covered in the last phase of their growth and the maturation with these bags. They're called banana sleeves. Normally, they're made out of conventional plastics. This project had the aim to verify the possibility to reach the same level of usage of the conventional one using biodegradable and compostable materials, so banana sleeves. In the project, it was proved that this is possible, and therefore the waste produces a compostable waste, and a compostable plant is for sure much easier to plan and to have than a recycling plastic plant. So with this, I finished my presentation. I just gave you a quite brief but hopefully useful overlook on how compostable materials and biodegradable materials can be used. Just before finishing, I wanted to present a project, European project. Many of you probably already know this project. The project is called SOIL, which is the acronym for biobased in soil application with optimal biodegradation in their ultimate life. The project has 18 partners in 5 member states, and there's we are a group of partner comprehending companies producing biodegradable materials, converters, academia, so researchers, and certification bodies. The aim of the project is to improve the circularity and the resource efficiency of agricultural application in a broader vision of the circular bioeconomy. Basically, we are going to develop 11 solutions, which are here, starting from mulch film, going through clips, twines, pheromone dispenser, turf nets, tree shelter, infill. So for different sectors, mainly agriculture, but also gardening, leisure, and sport, basically to try and improve the end of life of these materials, where we know that the end of life could be problematic. The project aims to reach for each of this project and to obtain for each of this project a material which is soil biodegradable. We're going to, for some of these materials, we're going to use enzymes to improve biodegradability, and we're going to improve their renewability up to 95%. So this is really a big step ahead to the state-of-art situation of materials. The project just started last year, so we are almost finished the first year, and I'll be happy to, if possible in the future, to present the results of what we are obtaining. For sure, it's a very challenging project, but hopefully it will bring solutions to growers and to the value chain, because the TRL expected for this application is between 7 and 8, so quite high TRL. This is my last slide. Thank you all, and obviously if you got questions, I'll be very happy to answer to them.
Thank you, Sarah. Perfect. Now, we take the questions later. We got a joint Q&A, so for those of you who came in late, please hold back your questions for so that we give space, first of all, to the second speaker. Patrizia is with us. I'm putting you, Patrizia, in the spotlight, and this is a good time for you to share the presentation.
Yeah. Thank
So
you.
if you join later this kind of setup, you can use the chat to type your questions anytime, but we will address them all later after Patrizia is finished with the presentation. Okay, thank you. Patrizia, you got the floor. Thank you for being here.
Okay, thank you very much for the invitation. So first of all, my name is Patrizia Schmidt. I'm leading the microplastics research at BASF in Ludwigshafen. And today I will talk to you about the fragmentation of soil biodegradable mulch film and how we can differentiate fragments that are released from such mulch films from persistent microplastics. So in the focus of my talk today, we will have the EcoVio M2351, which is our grade name for the soil biodegradable compound that we sell at BASF. We can measure the biodegradation of our mulch film in soil according to ISO 17556. And as you can see here, we can monitor the CO2 evolution over biodegradation time. And you can also see here that after 181 days, we reached 90% of biodegradation already, which is quite faster than needed for the certificate. But in the recent years, several questions came up. What are the remaining 10%? Could this be something persistent that remains in the soil? And this is why we started to look into that topic more in detail. And so in the past, we're working together with the ETH Zurich to understand where the carbon ends up of our biodegradable mulch film. And here in this specific case, we used a label, a 13C label that was introduced in different parts of the polymer chain. Here it is shown for the adipate. And we can then use the so-called nano-SIMS technique to find out where the polymer carbon ends up. You can also see here some images in the background. You see in light gray the biodegradable mulch film, and on top of that you see some linear structures that have been formed on that mulch film during the biodegradation process. These are fungi, and we also see some more spherical structures, which are microbes. And now I would like to show you the decisive picture. Here again you can see in the background, this time in green, the biodegradable mulch film. Why is it shown in green? It's green because this is the basis level of this 13C label that we introduced in the mulch film. And again, you can see the linear structures that have been growing on the film, the fungi, but these are shown here in orange and red. So why is this the case? The fungi took up the polymer carbon and used it to build up their cell walls. This is why we have an increase in the 13C carbon in those fungi structures, and that was for the first time then the evidence that the polymer carbon is not only converted into CO2, but also into biomass. But actually in soil we have a different persistence issue, and these are microplastics. So in the recent years, several publications came out that found microplastics of different origin in soils, and we wanted to understand where these fragments are coming from and if our biodegradable mulch film can actually be a solution for this issue. And to look into that aspect more in detail, I would like to explain to you shortly again what microplastics are. So microplastics are solid plastic particles that are smaller than 5 millimeters in size, and they are insoluble in water. And there are actually two different types of microplastics. One type are the so-called primary microplastics. These are microplastics particles that are already smaller than 5 millimeters from the beginning of their life cycle. And so they are intentionally added to the products. But these primary microplastics make up only a very small proportion of microplastics in the environment. The main proportion of microplastics in the environment comes from so-called secondary microplastics. And these are fragments that are released due to environmental aging and abrasion of macroplastics and are therefore unintentionally released. So this whole microplastic topic comes from the fact that these microplastics are persistent in the environment and therefore are not biodegradable. And this is why they accumulate and persist there. And so in our case, we wanted to demonstrate what is the difference of such persistent microplastics and fragments that are released from our biodegradable products. And this difference starts already when we look at the way how such fragments are generated. For example, if we look at a conventional mulch film, which is made out of LDPE, then such microplastics can only be formed due to mechanical abrasion or due to UV aging. And since these processes do not change the chemical composition of these LDPE mulch films a lot, these fragments that are formed are still not biodegradable and they remain and persist in the soil. In contrast to that, when we look at our certified soil biodegradable mulch film, then we also see that fragments are formed, but these are mainly formed during biodegradation. And this is also a process that we want to happen because we want, as soon as the material is buried in the soil, it falls apart, it's getting smaller and smaller because only then the microorganisms are able to take the polymer carbon up and convert it into CO2 and biomass. And to prove this aspect in a scientific way, we developed a method to extract such fragments from our biodegradable mulch film from soil. And this method is shown here. I don't want to go too much into detail here. It mainly works with centrifugation and the specific freezing and cutting technique. So if you're interested in the protocol, feel free to look it up. It's already published here. It is very important for us that we make sure for this protocol that we can efficiently recover all the particles that are contained in the soil. We also need to make sure that our particles are stable during the extraction because, of course, our biodegradable materials are very prone to biodegradation and also degradation by other ways. So this is something that we need to avoid here. And at the same time, we need to make sure that we remove a high proportion of the soil matrix so that we can then work with the so-called IR microscopy technique to analyze the remaining fragments in the soil. And with the IR microscopy, we have the big advantage that we can filter our samples and then determine the chemical composition and the size and the number of every single particle on the filter. And now I would like to show you a specific campaign that we conducted to analyze the fragmentation of our biodegradable mulch film. Here you can see that we worked according to ISO 17556 to monitor the biodegradation of our biodegradable mulch film. We also used cellulose as a positive control and LDPE as a negative control. But then we did not stop here, but we took out subsamples at specific time points of the biodegradation test. So at 10% biodegradation, 30%, 50% biodegradation, and then finally when we reached the 90% of biodegradation. And then we used our developed extraction technique to extract any remaining mulch film fragments from the soil and analyzed how many were still there. And here you can see an overview of the filters that we prepared for this test. You see in the beginning that we started with quite large mulch film fragments, and then with increasing biodegradation time, you can see already visually how the particles are getting smaller and that we also have less particles on the filter with increasing biodegradation time. And then we can summarize our results in several different ways. The easiest way to look just at the total particle counts over biodegradation time. And as you can see here, we started already with quite a high number of fragments per gram soil, so approximately 300 to 400 per gram soil. And then when the biodegradation starts, we actually even see an increase in total particle counts per gram soil. And this is because of that fragmentation process that happens. So as soon as the material biodegrades, it will fall apart from large pieces into a lot of small pieces. But then the good news is that these fragments that are formed are not persistent in the soil, but with increasing biodegradation time, the total counts also go down again. And if we look at the total particle mass over biodegradation time, then we see that this continuously goes down. So this is a very important point here to understand. So a high number of particles does not automatically mean that we also have a high polymer mass in the soil. And therefore, it is very important to understand these coupled processes of biodegradation and fragmentation. And now, if we go back here on this slide, you can see that we still found very few particles at the end of the biodegradation time, which corresponds also to a very small mass. Then we looked into these particles more in details. We found that the chemical composition of these fragments were still the same. They were much smaller than the original particles that we spiked. And we also saw that the molecular mass was already going down, which means that they just started to biodegrade as well. And then we wanted to understand if these, how long it would take until these remaining fragments would also be completely biodegraded. And this is why we started to work together with the UK Centre of Ecology and Hydrology, because they have developed a model for the fragmentation of originally persistent microplastics to find out what happens to them in the environment, but we could then apply this model also to our biodegradable mulch film fragments. And here you can see that we tried to compare the model predictions to our measurement results. Here are the particle size distribution at different time points of the biodegradation experiment. In orange, you see our measurement data, and the bar plots are showing what the model predicts. And in all the cases, the fits worked already quite well. And then we also compared the model CO2 evolution versus our measured CO2 evolution. And also here we had very good fits. And so we could confirm that the model works already quite well for our biodegradable mulch film, and we could then use the model to predict how long it takes until all the fragments are completely biodegraded. And here in this case, the model could predict that we reach that after 686 days. The other advantage that we have with this model is that we can not only look at specific time points like the ones that we measured, but we get continuous particle size distribution. And so we also learn when we have the peak of the fragmentation. So now that's all what I have for today. I wanted to mention again that we specifically developed this method to understand how fragmentation of biodegradable materials work, not only for the mulch film, but also under industrial and home composting conditions. We already did quite a lot. So we are working here with a combination of biodegradation tests that are standardized, extraction and analysis via microscopy, and in addition now also with this fragmentation model to really understand and prove that these fragments that are generated from biodegradable materials are not persistent compared to polyethylene, for example, that will release persistent microplastics that will stay in the soil and accumulate there. So thank you very much. And I'm looking forward to a fruitful discussion.